Welcome to qnawire.
Okay, so we know the heat conduction can be equal to Ka times delta T over L. K is the thermal conductivity, A is the section area, and delta T is the change in temperature, and L is the original length. In this case, we use the thermal conductivity of copper, which is 385 watts per meter times Kelvin. It's because the one end in the boiling water is made out with copper, and the heat is flowing from the boiling water part to the ice texture part. Okay, and the section area is given as 4 centimeters square, which is 4 times 10 to the power negative 4 meters squared. And the changing temperature is from 65 degrees Celsius to 100 degrees Celsius, which is 35 Kelvin. Okay, and the original length was given as 1 meter. Therefore, we can plug in back to the equation to determine the heat conduction rate, which is H equal to 385 watts per meter times Kelvin, and then times 4 times 10 to the power negative 4 meters squared, and then times 35 Kelvin over 1.00 meter. Okay, and this will give us the heat conduction rate is about 5.39 watts. And for the next question, well, we know the heat conduction can be equal to Ka times delta T over L. Therefore, length L can be equal to Ka delta T over H. So L2 can be equal to K2 times A times delta T2 over H. In this case, K2 is the thermal conductivity of the steel, since L2 is made up with the steel. Okay, and the thermal conductivity for steel is 50.2 watts per meter times Kelvin. And they share the same section area from the last question, which is 4 times 10 to the power negative 4 meters squared. And the changing temperature is from 0 degrees Celsius to 65 degrees Celsius, because the steel part is made out is in the ice texture. Okay, so in the ice, the temperature is 0 degrees Celsius. If we convert to Kelvin, we have 273 Kelvin. And if we do some calculation here, we'll find out the changing temperature is 65 Kelvin. And from our last question, we know the heat conduction rate is 5.39 watts, because these two parts share the same heat conduction rate because they were connected with each other. Okay, so we can just use the heat conduction rate from the last question. So therefore, we can determine the L2, which is equal to let me see, K2, which is 50.2 watts per meter times Kelvin, and times 4 times 10 to the power negative 4 meters squared, and times 65 Kelvin over 5.39 watts. And this will give us L2 is equal to 0.242 meter. And these are the answers for this question.